Yeah, so welcome everyone to Quantum Science Seminar episode number 33, I believe we are. And today is our very special second Young Researchers session. And we have three young researchers that we selected from a list from a great lineup of applicants. And maybe you keep in mind that we will probably repeat this again, and we encourage everyone, of course, to apply. And what remains to be said, as usual, I want to remind you to send questions that come up during the talks to our email address, quantumscienceseminar@gmail.com, or directly in the YouTube live chat. And then we are ready to start. The first talk will be by Jessie Zhang, and it will be about the assembly of a single rovibrational ground state molecule in an optical tweezer. And with this, I will hand over to Jessie.
Okay, so can everyone see this? Okay. Yeah, so thanks to the organizers for inviting me to present at this session, and thank you for all being here. I'm Jessie, and I'm a graduate student working in Kangkwan Ni's lab at Harvard University. And today I would like to talk about some very recent results in assembling a single rovibrational ground state molecule in an optical tweezer. So what you're seeing here is actually the objective that we use to form our optical tweezers, and imaged through this is a sodium mott. And surrounding this are large magnetic field coils, which we actually use in the process of the molecule formation. Before I delve into things, I would first like to acknowledge the team that I work with. So our PI, Professor Kangkwan Ni, and for the majority of results I will be talking about, it was completed together with postdocs Will and Young Wei, as well as fellow graduate students Louis, Yichao, and Kenneth. And Jeremy Hudson from Durin also provided us with some theory support. So our motivation is a broad goal that drives many efforts in quantum science today, which is to create a quantum system that is together fully controllable in all its quantum mechanical degrees of freedom, scalable up to large sizes, and capable of producing entanglement, which can then be used as a resource in, say, quantum information applications. And many platforms are being used to pursue this goal, including many of which have been covered in various talks in this seminar series. And we've already seen how a lot of these have already shown exciting applications in quantum computing and quantum simulation studies. And what we would like to do is to expand the toolbox of quantum control in the field to single ultracold molecules in optical tweezer arrays. So why are we interested in doing that? Well, ultracold molecules offer many unique properties, and two particular ones that stand out in the case of quantum science applications is their rich internal structure and their inherent tunable long-range electric dipole-dipole interactions in the case of polar molecules. And there have been a lot of proposed applications using these ultracold molecules to, say, form quantum gates for quantum computing or to simulate quantum many-body Hamiltonians. And common to a lot of these proposals are systems involving ultracold molecules that would ideally satisfy certain requirements. So for example, we need single molecules to be pinned individually in sites. And for the entangling interactions, one needs to have control over the exact internal state of the molecules. And in particular, these internal states need to have a large electric dipole moment. And as with most quantum systems, large coherence times is desired. And since this dipole-dipole interaction is highly dependent on the interparticle distance, ideally one would also want these in the lowest motional state to minimize decoherence. And in addition, to realize these proposals, one also needs to be able to prepare and address individual molecules. And a lot of previous work on neutral molecules has been done on this front, including creating bialkalis, whether in bulk gases or optical lattices, and also direct laser cooling of molecules. And in addition, for example, microwave and electric field control of these molecules in the ultracold regime. And a lot of work here has already laid the groundwork for many of these requirements listed here to achieve these applications. But I'd like to draw your attention to the last key ingredient here, which is preparing and addressing the individual molecules, meaning that we really want quantum state control at the individual particle level. And in particular, this is where we think optical tweezers can come in. So we've already seen a lot of talks in this seminar series where large numbers of single neutral atoms can be trapped and manipulated to form defect-free arrays with flexible geometries. And these optical tweezers naturally offer single site imaging and addressing and offer really good single particle control. So seeing these advantages that optical tweezer system provide, our goal was to bring the single particle control offered by optical tweezers to the world of molecules. And in this talk, I would like to show you that we have achieved a single fully quantum state molecule in an optical tweezer. And by fully quantum state controlled, I mean that we know its exact internal and external state, and ultimately these molecules will be capable of generating entangling interactions as many proposals envision as a starting point. So our approach to single molecule control in optical tweezers is a bottom-up approach, which is shown schematically here. So we want to start from single atoms where the full quantum state control is relatively mature, and prepare them in internal and external states before forming molecules from there. And I should mention, one could also go about approaching this by direct cooling and trapping of molecules and doing all the quantum state preparation on the molecules themselves. And indeed, there have recently been very large advancements in this approach and have also shown a really great promise towards full quantum state control. However, for this talk, I will be focusing on this bottom-up approach presented here. So just to be a little more specific, our atoms of choice are sodium and cesium, which forms a bialkyl molecule that has one of the largest electric dipole moments. So shown here are a single sodium and a single cesium atom trapped in individual optical tweezers side by side. And in addition, previously our group had demonstrated the ability to cool both species to their individual ground states in their independent traps, and then adiabatically merge to a single trap with very high fidelity. So for the work that I will be talking about, which is this molecule formation step, the starting point is two ground state cooled atoms co-trapped in a single optical tweezer. And so then the crucial point now is that this molecule formation process needs to maintain the low entropy of states that the atom pair starts out in, so that we can effectively map our very fine control of the atoms that we worked so hard to obtain previously, and map that onto the molecules. So how do we do that? So we start off with two atoms co-trapped in an optical tweezer, shown here, and we would like to end up in the rovibrational ground state. And this is shown on a potential energy curve. And the reason we want to go to the rovibrational ground state is, for one, it's the most stable, and also because it has the largest electric dipole moment. And so this can be done in a two-step approach. So in particular, we first create a weakly bound molecule by a process known as magnetoassociation. And then we drive a coherent optical transfer from this weakly bound molecular state to the rovibrational ground state through an excited electronic state. Now, this two-step approach is kind of necessary to bridge this large mismatch in both size. So mind you, this is log units, as well as the large mismatch in energy. So like this thousands of Kelvin needs to be dumped somewhere in this process that doesn't introduce additional entropy. And this is actually a well-established approach for bialkalis, and we are really standing on the shoulder of giants in our attempt of this approach. And here we do it for the first time on the molecule sodium cesium. And in addition, we're doing it for the first time in optical tweezers, which really puts us in a different parameter regime. So I'll discuss each of these steps in turn. So first is the creation of a weakly bound molecule by magnetoassociation. So I won't go into too much detail about the specifics, but it suffices to know that the process uses an avoided crossing that arises by a Feshbach resonance that occurs between an atomic state and a molecular bound state. And in particular, by sweeping the magnetic field, we can adiabatically convert from free atoms to a bound molecular state and vice versa. And for the particular choice sodium cesium, we find such a resonance at around 864 Gauss. So over here, we see that we can adiabatically convert from the free atoms on the right to a weakly bound molecule on the left when we ramp across this particular magnetic field. So the specifics of how magnetoassociation how it works isn't super important here, but what is relevant to us in terms of quantum state control is how it maps the relevant degrees of freedom to the atom pair to the resulting molecule and system. So what do I mean by that? So the relevant degrees of freedom of an atom pair in an optical tweezer can be separated into its center of mass motion and its relative motion. And both of these are quantized in the harmonic trap. And it turns out that this magnetoassociation process kind of neatly maps the center of mass motion of the atom pair onto the center of mass motion of the molecule, which corresponds to its external degree of freedom. Whereas the relative motional state is mapped onto the internal degrees of freedom, including the rotational and vibrational state. And in our particular case, the specific resonance we are using maps atom pairs in their relative motional ground state to a molecule in a rotational ground state. And the center of mass motion of the atoms carries over to the external state of the molecule. And so by virtue of this process, the internal state of the molecules we create are pure. Whereas if we want to know the external state of the molecule, we just need to know the center of mass motional state of the atom pair. And that we can do fairly straightforwardly by thermometry on the atoms. And so when we do that, we find that roughly 77% of the weakly bound molecules that we form are in the motional ground state. And this is significant because in some sense, we are cooling and preparing the atoms, but that effectively means we're cooling and preparing the molecules. And it means that we're mapping our control over the internal and external states of the atoms onto the molecules. And so at this point, in principle, we already have a fully controlled molecule in our optical tweezer, and we could call it a day. However, these molecules, as I mentioned, as is, are quite weakly bound, and they don't have a very large electric dipole moment, which I mentioned is necessary for most sorts of applications. So for that, we really need to further transfer to the rovibrational ground state. And this is done by a coherent 2-photon transfer process going through an excited electronic state. Now, I won't bore you with all the details of how we determine these states, but suffice it to say that we did spectroscopy to identify suitable states, including both in the excited and the ground states. So we can, for now, just forget about these potential energy curves and abstract these states out. And what we have is essentially a 3-level system. So 2 ground states and an intermediate state with some scattering. And we want to drive from this weakly bound molecular state to the rovibrational ground state. And when there's a 3-level system like this, we can drive a 2-photon transition between the 2 ground states by locking 2 lasers whose energy difference matches the energy difference between these 2 ground states. And typically one detunes some distance away from the intermediate state to avoid scattering. So in our experiment, we do just that. So we lock our lasers. And when we scan the pulse time, what we see are actually Rabi oscillations between this weakly bound molecule and the rovibrational ground state. So this is really exciting because we're really coherently flopping between 2 internal states of the molecule. And bear in mind that these 2 states are roughly 7,000 Kelvin in difference. So this is really exciting. We have a row vibrational ground state in our optical tweezer. And now we want to characterize some of their properties. Well, first of all, we're interested in the lifetime of these molecules in the optical tweezer. So we form the molecules, wait some time, and measure their survival. And we measure a lifetime on the scale of seconds at the normal trap powers we operate at. When we increase the tweezer power, however, we see a decrease in lifetime. And so this is consistent with it being limited by photon scattering from the tweezer light. But this lifetime, we believe, is long enough for the quantum computing and simulation studies that we are after. And finally, going back to our business of quantum state control, we want to know how our state purity fares out in this whole transfer process. So our two-photon process resolves the hyperfine states. So we are in a designated internal state, no problem. Whereas for the external state, the optical transfer process does give some additional heating on the molecules that we need to consider. And when all of these are factored in, we estimate that roughly 65% of the row vibrational ground state molecules we form are also in the motional ground state. So what this is saying is that having started from a single atom pair, we end up in a well-defined quantum state of the molecule, and this includes both its internal and external states. And that's significant because it means that we can now use these individual fully controlled molecules as entities to study, say, quantum many-body systems or to perform quantum computing. And so that leads me to my conclusions and outlook. So we've assembled a single fully quantum state controlled sodium cesium molecule in its row vibrational ground state in an optical tweezer. And this was done in a two-step process that maps our full control of the atoms onto the resulting molecule. Now, if we go back to our molecule assembly scheme that I had showed earlier, what we see is that this molecule formation step actually concludes the whole process. So we've laid out an entire recipe to assemble single atoms into single molecules in optical tweezers in a very well-controlled manner. So we can now treat this as a black box, which we call the Ultracold molecule assembler. And by simply expanding this to arrays, we can start using this for all the exciting quantum computing and simulation applications that have been proposed but not yet realized. Which leads me to my outlook and some ongoing work. So as I mentioned, we need to expand to arrays. So this is work in progress. Shown here are 10 cesium atoms loaded and cooled to their motional ground state simultaneously. And ultimately, we will want to generate entangling interactions with these individual molecules and really start utilizing the rich properties these molecules have to offer. Yeah, so with that, I would like to thank you for your attention, and I'm happy to take any questions.
So thanks, Jessie, for this beautiful talk. Actually, there are quite some questions. So the very first one is, in the introduction, you talk about the rich internal structure of a molecule. What do you mean by that?
Right, so yeah, so like normally an atom, it has internal state, but it's like, say, hyperfine and fine structure and such. But for molecules, there are additional degrees of freedom, such as vibrational states and rotational states. And these lead to really rich features that can come out of these molecules.
So another question. So would you mind to repeat how long takes the sequence of preparation of these molecules?
Oh, yeah. So that's actually something I did not mention. But so we load our atoms directly from a MOT, and then we do the cooling. And so that the loading and cooling process is on the order of like 10 milliseconds or so. And then to form the molecule, that's on the order of like 100 or 200 milliseconds. So mostly because we need to ramp a large magnetic field. But overall, the duty cycle is like 1 or 2 hertz.
So another question, so in this preparation sequence, what are the most sensitive parts of it, and what limits the final yield of molecules that you can get in this rovibrational ground state in the current experiments? So what is more sensitive, the preparation and cooling of the atoms, or the optical transfer of the molecules to the right state at the end?
All right, yeah, so at the present moment, it's actually this first step of converting to the weakly bound molecule. And because this step is really kind of a filter for the motional states of the atoms, because it really only selects out those atom pairs in the relative motional ground state. And that, so as you can see, the conversion efficiency over here is between 40 and 50%. And that is limited by technical reasons right now. So we cool the atoms to their motional ground state, but in our particular apparatus, when we were running this experiment, the merging process did introduce some additional heating. So the limiting factor is this first step. So this conversion is like 80 to 90% efficient. Yeah.
And maybe just the last question, when you optically transfer the atoms to the ground state, so what is different, better, worse, different than in bulk gases in tweezers?
Right, so there, one thing is actually, so I mentioned our conversion efficiency is 40 to 50%, and it's actually not optimized yet, but that is actually already one of the highest conversion efficiencies directly going from atoms to a weakly bound molecule. And that, so in bulk gases, generally this step is limited by like 3 body collisions. But in an optical tweezer, we can cleanly prepare 2 atoms. And I believe in optical lattices, it's also similar because it's really difficult to load your optical lattices in such a way that you end up with one of each species exactly. So optical tweezers, it's a really clean system because we can prepare exactly 1 atom of each. And yeah, so I would say that's a large advantage.
And I said it was the last question, but just a very last one came up. So how do you detect these molecules? So do you use fluorescence?
Oh, right. So I actually, I didn't really discuss this, but because all these processes are coherent or like adiabatic, so what we do is, so we convert from atoms into molecules, and to do detection, we actually reverse this whole process. So we convert the molecules back into a weakly bound molecule, then back into the atoms, and we detect the atoms. So this process is completely reversible. And that allows us to not have to rely on molecular properties to do any imaging.
Okay, so thanks a lot. I think we have to move on for the sake of time.
Yeah, thanks, Jessie, also from my side. And we move on to the second speaker of today. That is Ryan MacDonnell, who is actually calling in from Australia. So it's our first speaker who is giving the quantum seminar in quantum science seminar really in the middle of the night. So thanks, Ryan, to do so. And his talk will be about analog quantum simulation of chemical dynamics.
Thank you, Christian. 1 second. All right, hopefully that's working properly. So I'm going to talk about a recent paper that we posted onto the archive on analog simulation of chemical dynamics. And yes, I am coming to you from Australia. It is tomorrow, as I like to say. So I'm very getting used to adding 1 to the date to everything that's scheduled. So yeah, the main thing that we want to simulate here is, so in general, we're looking at chemical reactions. And I think it's not controversial to say that chemical reactions are governed by the dynamics of both the electrons and the nuclei. But one of the main underpinnings of quantum chemistry is what's known as the Born-Oppenheimer approximation. And so basically what this is taking both your molecular wave function and your molecular Hamiltonian, so this is the non-relativistic Hamiltonian, and splitting it into an electronic and a nuclear part. And so here, small r is electronic degrees of freedom and large r is nuclear degrees of freedom. And so by doing this, now you can solve what's known as the electronic Schrodinger equation. And what you get out of this, the eigenvalues, are what we call potential energy surfaces. So on the right here, we have smooth surfaces as a function of our two different coordinates, R1 and R2. So these are changes in the energy of the molecule as a function of this. And so this is a really powerful concept in chemistry. In many different types of reactions, we can use potential energy to predict things like the probability of a transition between different geometries. So for example, just a spinning about this central bond using something known as transition state theory, for example, or predicting the thermodynamics of different reactions on a single electronic state. However, in certain cases, the Born-Oppenheimer approximation fails pretty catastrophically. So particularly in cases that involve multiple electronic states. So if you excite a molecule to a higher lying electronic state, then its passage back to the ground state can involve what's known as a conical intersection. And so there you have a coupling between these two electronic states that the Born-Oppenheimer approximation assumes is zero. And so in order to account for this, you really need to include a coupling and include cases where you have ultra-fast dynamics with things happening on the order of femtoseconds to picoseconds. So you don't have really the ability to have this thermal averaging that you get with single ground state calculations or single ground state reactions. And so an accurate simulation of that requires some quantum mechanical treatment, both of the nuclei and the electrons. And so there are many different ways of doing this. During my PhD, we used a lot of, we used potentials that you get from the Born-Oppenheimer approximation. These are what we call adiabatic potential energies. And really in quantum chemistry, when we say adiabatic, it almost exclusively refers to Born-Oppenheimer potential energy surfaces. And so these are diagonal elements of the potential. But as I said, there is a coupling between states, and this is actually an off-diagonal element known as the non-adiabatic coupling. But as you can see, this is sort of an ill-behaved surface. We have cusps on this surface at the point of conical intersection. And if you were to look at this coupling element, it is actually singular at this point because it's inversely dependent on the energy difference. So this is a bit ugly to deal with for a simulation. So an alternative approach is to use what's called a vibronic coupling Hamiltonian. So here we make a transformation from an adiabatic regime to a diabatic potential energy surface, which has also a coupling surface of potential. And this is just a unitary transformation. What's nice about this is that in many cases, when we start with some fairly complicated looking surface, we end up with something that can simply be represented by a low order Taylor expansion. And so that's what I'm showing here. We have our on-diagonal harmonic oscillator term, and then we have a set of, we have this Taylor expansion, which includes elements of each of the states or pairs of states, electronic states, I should say, as well as different motional degrees of freedom. And so for most of what I'm talking about today, we'll just be talking about the linear vibronic coupling. So this is truncating this Taylor expansion down to the linear terms, although you can go to higher order terms. And so, as I mentioned, we want to look at nuclear dynamics. And this is already, understandably a difficult problem just at the electronic level. So you can imagine adding in nuclear dynamics as well makes this a difficult problem for classical computers. So with quantum computers, there's been quite a bit of news recently of all the different methods that have been tried, just looking for electronic structure properties, for example. And there have been several proposals for doing time-dependent simulation. So treating electrons and nuclei on the same footing, or using a vibronic coupling type of approach, or doing variational hybrid approaches. But so far to date, there haven't really been any demonstrated time-dependent approaches that are quantum mechanical in nature. And so instead, in my group, what we have looked at is using an analog simulation technique. So classically, an analog simulation you can think of as just modeling some complex system using some system that you can easily control in a lab. So a wind tunnel or a wave pool or something along those lines. And quantum mechanically, it's exactly the same thing. You just map your desired Hamiltonian of your system onto some controllable quantum system. And there's been some recent developments, both with analog simulation as well. So, for example, there have been recent proposals of electron structure with optical lattices, or using photonic chips and boson sampling for vibrational and Frank-Condon spectra. And I should also mention, recently Rob Shulkov's talked about the boson sampling experiment with circuit quantum electron dynamics. So there's more on that from the quantum science seminar. And so the regime that we're using is what we call a MixedCuted boson quantum simulator. So this is any architecture with both internal degrees of freedom and bosonic degrees of freedom. So here I've shown it as a qubit or n qubits, but really this can be any qubit system and some number of bosonic degrees of freedom. And the mapping that we make is taking the electronic degrees of freedom of the molecule and mapping it directly onto the internal states and mapping vibrational degrees of freedom onto bosonic degrees of freedom. And so just to give a couple examples of these, for example, ion traps within the trap have motional degrees of freedom, and they have their internal states, which are usually the qubit states or qubit states. As well as circuit quantum electrodynamics, which I mentioned last slide. There they take sort of more of a digital looking approach, where you have a superconducting qubit that's coupled to a microwave resonator. So again, you have the same 2 degrees of freedom. And so to give you an idea of how this mapping works, I'm going to walk through step by step how we map the degrees of freedom of pyrazine, this molecule here, onto a single trapped ion. So to begin with, we map the energy difference roughly corresponds, so between electronic states, that roughly corresponds to the internal energy of the qubit of the trapped ion. So here I've just represented these states as different orbitals, but more generally, these are multi-orbital states. The harmonic degrees of freedom of the molecule, here I've just shown 2 of them. So these are the 2 that are most important for pyrazine. Those we can map onto the vibrations of the ion within the trap. And then our additional terms, so our tuning and our coupling term, which are these different terms that entangle electronic and nuclear degrees of freedom, those take the place through, in a trapped ion, what was known as a sigma Z gate and a Mulmer-Sorensen gate. So these are different types of interactions that lead to the same type of coupling term that we want to see for the molecule. And by introducing these laser fields, we also get an AC Stark shift, which acts on the sigma Z component, and a laser detuning, which acts on the ion vibration component. So in the end, we get these 4 different types of tunable parameters. So experimentally, you can tune each of these in order to obtain the same Hamiltonian as the molecule. And so generally, what a simulation looks like is initially you start with, say, a molecule in the ground state, both motional and electronic. And you can prepare your initial state by, say, preparing that initial qubit state, but also by having a displacement. So in certain cases, it's beneficial to displace the entire model one way or another. And then when you essentially activate the Hamiltonian, when you add in these coupling terms, you get evolution on some on the time scale of the simulator. And at some certain time, you can stop and measure what is the output of different observables. So the example I've shown here is just measuring the state of the qubit, which corresponds to an electronic state. And so because of the difference in the frequencies of the simulator versus the system that we want to measure, there's this large scaling factor in time. So whereas the system time that we're looking at here for pyrazine only takes, like the dynamics that we're looking at only takes place over the course of 400 femtoseconds, that's around 16 milliseconds in an experiment. And so because this is a quantum simulation, you're doing an average over many different experiments. And so from a single experiment, you just get a 1 or a 0. By doing this with a time scan, you get a set of 1s and 0s. And by averaging over many different experiments, you're converging onto this population that you would expect to see. Now, if we want to go beyond the 2D linear vibronic coupling model, we really need to think of how this scales, first of all, from what I've shown. So classically, doing this the simple conventional way is it scales exponentially as expected, but there's actually a classical technique known as MCTDH, which is extremely powerful, but is also highly system dependent. So we can't add to first approximation we can't predict exactly how that's going to scale from one system to the next. However, if we look at quantum techniques and we compare them here on a linear scale, we can see that using qubits, we still get linear scaling. However, the prefactor is quite large. Whereas with our technique, because we have this one-to-one mapping, we're really going much easier on the resources. So we're taking a lot advantage of using these continuous degrees of freedom. And so if we want to go beyond this model, we have to consider a couple of extra things. One of them is that, so if we want to look at, say, n-trapped ions, that gives us access to 3 n modes and 2 to the n states. As a theorist, it's really tempting to just tell my experimental colleagues to, use this many lasers, but unfortunately lab space is finite. So one way around this is to use Suzuki-Trotter expansion. And so now with the Suzuki-Trotter expansion, we're actually looking at our t, in this case, being our time. And so for anyone who's not familiar, in a Suzuki-Trotter expansion, when you have an exponential of some sum of terms, you can approximate that as the product of exponentials repeated over a certain number of time steps. And this gives us the potential of using the same laser for multiple terms within the Hamiltonian. In addition, we can simulate system-bath interactions. So I'm a bit short on time, but basically doing an exact simulation involves, on a classical computer, involves solving a master equation, which further increases the difficulty. And so one thing that we can do is we can do a simulation with a Lindblad superoperator, so having cooling and heating terms on the vibrational modes. And that just so happens to correspond directly to laser cooling and heating. So we get a set of parameters that we can optimize for specific temperatures and specific coupling strengths. And here, all that I'm showing is that if we look at something that's optimized for a certain temperature that's typical of a molecule, say room temperature, then if we just say take an average of this phonon number, we don't really see a difference in the populations. So because this KT is much less than the frequencies involved, it's actually not strongly dependent on whether or not you use the average. So really you can get away with using, say, something that's optimized just to some low temperature, much less than the frequencies. So I'm just going to skip over this. This is just higher order terms are possible. That's all I'll say here. And so what I've shown today is that vibronic coupling models, we can map them directly onto these Qubit bosonic simulators because of this one-to-one correspondence between internal and electronic and vibrational and bosonic degrees of freedom. And in fact, these first order terms correspond directly to existing multi-qubit coupling schemes. And we can extend this, as I said, by using Trotterization and by adding in these system-bath couplings. And really quickly, I want to thank the great students that have helped me out with this. Claire Dickerson derived a lot of the initial pyrazine experiment. Claire Birch was responsible for looking at the system-bath couplings, and Ala Kumar worked a lot on the Trotterization. So thank you.
So thanks a lot, Ryan, for a beautiful talk. So we have some questions. So the first one is the following. For the types of chemistry problems that you are looking at, with which level of quantitative accuracy do you need to do the simulations if you want to calculate something useful, that is something that is not possible for current classical simulations?
So which level of quantitative accuracy? Well, this strongly depends on, say, the potential. So if I go back to this, go back to this, this scheme here. So what we see is that for doing something that beats, say, any classical algorithm, it's actually quite tough. We're pushing up towards potentially hundreds of modes for a system. However, there's the potential for systems more around tens of modes or so on. And so in order to obtain something that, say, is a quantum advantage, really what we need is, going to things with, say, an open quantum system and looking at master equations with, say, on the order of 10 modes or so. And at that point, even from fairly short dynamics, if you have dissipated dynamics, you can start getting useful observables. So one thing I didn't mention is looking at vibronic spectra. So having this coupling gives basically quantitative accuracy with vibronic spectra that you can predict. So hopefully that partially answers the question.
So another question we have is, you have presented this model for simulating pyrazine. So what is the specific interest of this particular molecule you gave us?
So pyrazine is sort of like the hydrogen of vibronic coupling models. So it's really well represented with just 2 modes for sort of qualitative accuracy. If you want to go to quantitative accuracy, the LVC model is I think 6 modes, and then the full molecule has something like 24 modes. But just that qualitative accuracy of getting the right type of dynamics and seeing the right change in population and spectra and so on, you can get that just out of 2 modes. So it's a nice, simple model system that is really easy to go to.
Okay, and very last question. So about your mapping. So you explained the mapping of the molecule to a single ion, but it involves entangling operations. So how many ions do you need in the chain, or can you do it only with 2?
So you can do it with just 1 ion in the case that I showed. So you're using these, nominally these are Mollmer Sorensen and sigma Z gates, but you're not actually using those to entangle between different ions. You're using them for the coupling between the internal and motional degrees of freedom. So you can do it with as few as 1 ion. And in fact, it can be advantageous to use just, say, a single ion, because otherwise you have to balance out this, the entanglement between ions with the entanglement between the degrees of freedom.
So thanks a lot, Ryan. I think for the sake of time, we have to stop here and move to the next speaker.
Thank you.
Yeah, thanks also from my side, Ryan. Next in our lineup today will be Gonzalo Carvacho, and he will talk about experimental violation of N locality in a star quantum network. The stage is yours, Gonzalo.
Hi, everyone. I hope that it's working. So, well, first of all, I'd like to thank for the opportunity of presenting this work entitled Experimental Violation of N Locality in Star Quantum Network. So my name is Gonzalo Carvacho, and I'm working in the Quantum Information Lab at Sapienza University of Rome. So, well, this work was published last year and was a collaboration between the International Institute of Physics in Brazil with Professor Rafael Chavez and the Quantum Information Lab at Sapienza University, led by Professor Fabio Charrino. Okay, so in this work were involved several PhD students and also postdocs. Well, this work is very connected with the field of causal inference. So with causal inference aims to decide which causal models are compatible with the observed data that we are trying to prove, right? So the idea is when you are entering through the laboratory, you are performing some measurements, and in the case of photons, you typically have answers which are zeros or ones, and then you process this data and compare with the model that you were working before. So the idea of the experiment that I'm going to show you is to check if correlations, quantum correlations, belong to the model that we are going to present here. So first, I would like to introduce some definitions. The first one is the one of directed acyclic graphs, so the DAGs. And typically you have nodes. In this case are two circles, A and B, and you can call them Alice and Bob in the case of communication protocols. And you have an arrow. So the arrow is going to take into account the causal effect that is moving from Alice to Bob in this case. So we are not going to consider models such as this one, where you can see that there is a cycle, because you cannot decompose the probability distribution according to the Markov rules. Okay, so another elements that we are going to consider are going to be the hidden variables that are going to be represented by these red squares with the lambda, the measurement settings by these green squares, and also the measurement outcomes. So if you consider all of these elements, you can construct these structures, which are called causal structures. And in particular, this is a very famous one because you have one hidden variable, two nodes, two measurement settings, and this is the Bell causal structure. So the idea of introduce the directed acyclic graph is because you can observe this graph and you can obtain some information from this DAG. For instance, the fact that there is no arrow between X and Y means that there is no communication between the parties. So you have to separate this. So in the experiment of Bell that was realized like 3 or 4 years ago with the loophole-free Bell test, they have to separate the parties in order to ensure that they were satisfying the locality constraints, right? So you can observe that conditions by checking on the graph. And then you can also perform the distribution of the probabilities that you can obtain here. Okay, so for instance, in this case, which is the Bell case, if you consider dichotomic measurements at each party, Alice and Bob, you can obtain a classical bound, which is upper bounded by 2, okay? And well, if you consider also all these elements, hidden variables, measurement settings, measurement outcomes, you can construct different models. This is the instrumental causal model, very important. There are some other models, which is, for instance, this one, which is a complex model of linear chain networks, and also the star-shaped network that I'm going to present in these slides. So the application of the Bell inequalities are very wide. They move from quantum information and quantum foundations to the quantum generation of random numbers. So in this case, you can see that the experiment that we perform can be exploited for generation of random numbers, for quantum communication protocols, and so on. So since it's an experiment related with the networks, in order to have a networks, you would like to have at least 3 nodes. So we're going to say that we have 3 nodes when you have 3 of these circles, the blue circles. So you have Alice, Bob, and Charlie. And the first experiment that were done considers just only one hidden variable. Okay. So in this hidden variable, they subsume all the information of the system. The thing is, you can obtain also the probability distributions, and you can obtain, according to this, an inequality that can be violated if you consider quantum system. Okay. So if you go to the photonics experiment, you will have 2 photons entangled, and these photons that are generated, if you have 3 parties, you will need at least two crystals. So each crystal is going to generate 1 couple of photons, and hence you have 2 physical crystals that you subsumes all the information into just one hidden variable. So if you do that, it's okay. You can obtain an inequality, and then you can obtain the probability distribution and violate the inequality. What happens later is that people said, look, maybe we can consider that the crystals are different. So we are going to set lambda1 and lambda2. And what happens in that case is the fact that you can construct another model. So it's a completely different model because the outcome depends in different situations. For instance, in this case, Bob is going to depend on what happens with lambda1, lambda2, and also the measurement settings in epsilon. While in the local model, there is just one hidden variable. So more or less the distribution of the probabilities is different. The inequality is different. And hence, if you perform a violation of this in this network, which is the simplest network, you can obtain some correlations that are truly new with respect to the local ones. Okay, so the first experimental implementation of these networks in order to violate the bilocality were done in 2017, one in Rome and the other one by the group of Pride. So they exploited one laser and two different crystals for the violation of the bilocality in this simple causal structure. And they obtained the violation of bilocality, and they show also the fact that this is completely new with respect to the locality one. In 2019, the group of Zhang Wei Pan was able to perform the violation of bilocality under strict locality constraints. So it means that they really separate the parties. So Alice, Bob, and Charlie were completely separated in order to ensure that there is no communication between them. And in this way, the correlation cannot be explained in that way. Also, he exploited two different lasers. So that was a very nice experiment. All of these three experiments, so those of the 2017 and also the one of 2019, exploited Bell state measurements in both stations. Okay, so they exploited the beam splitter in order to perform these measurements. So they had to synchronize the lasers. What happens in 2017 was proved that you can perform also the violation of bilocality by exploiting only separable measurements, which is very easy with respect to the Bell state measurement. So this is something very good. So now we're going to move to the end locality. So let's check for the bilocality case. So in the bilocality case, you have three nodes, A1, A2, and Bob. You have three measurement settings and two crystals generating a couple of entangled photons. Okay, the distribution of the photons is in that way, and you can obtain the inequality that you would like to violate in order to ensure that you are working within a quantum regime, and you can obtain these expectation values, and then you can obtain also the measurement settings in order to perform this violation. So when you go to the end local case is when you are increasing the number of nodes and also the numbers of resources, the quantum resources. So in this case, for instance, you have 4 quantum resources and you have 5 nodes. So this is a particular case of the star network. So you can see that each of these sources is generating a couple of photons. One of these is going to each station, A1, A2, A4, and so on. And the other one is going to be directed to the central node. So this central node is the one of both. So all of them are performing the measurements in this place. So Bob has access to all the measurement settings. Well, in this, something important is that all the inequalities make the assumption that the sources are completely independent. So this is something that you have to ensure if you would like to check for this model. And something else is the fact that the optimal violation can be obtained through separable measurements. So this is very good because you are not restricted to the fact that you have to perform Bell state measurement if you would like to arrive to the maximum value. Well, so let's move to the experimental side. So in this case, you have that we exploited 4 different laboratories in order to ensure that the separation of the parties. We have A1, A2, A3, and A4. At each laboratory, you will find that there is a laser and also a crystal generated entangled photons. You will have the Bob station is going to be contained in the laboratory 1, and hence all the laboratories were connected with optical fibers. So in this case, what you have is this setup, this experimental setup. So all the sources are sending 1 photon to Bob station, and the other photon remains into the same laboratory in order to be measured. The separable measurement means that you don't have to perform the Bell state measurement, and hence you can perform the measurement through halfway plate, polarizing beam splitter, and single photon detectors. Okay, so you have 4 independent entangled sources, 4 independent lasers, 5 time taggers in order to check for the coincidence between all these photons that are moving around. And in some cases, we perform up to 1024 separable measurements to perform one violation. Okay, something good is that we can change the violation, the coincidence window in order to increase or decrease the number of events and hence obtain the optimal violation. Something pretty cool is the fact that the upper bound of the inequality doesn't depend on the number of nodes, but depend on the number of measurement k. Okay. So the experimental results, you have the measurement settings A1, A2, A3, A4 perform 2 different measurement settings, for instance, in the case of k equal 2, while both perform 2 if all of them are doing the same number of k. So here you can observe the different violations obtained for the different number of sources and for the different number of measurements. So in the case of 2 measurements at each party, and for 2 sources, we obtain this violation. The red line represents the classical limit, while the black line represents the maximum value that you can obtain through the quantum framework. This is the expected number that you're supposed to obtain because in your experiment you have noises. So that's why you cannot reach to the optimal value. Okay. In the pictures, you can see 2 different sources that were exploited. One was a BBO crystal and the other one was a PPKTP crystal. Okay, so within this experiment, we were able to show no classicality demonstration of the implemented networks. So you have here, these points represent experimental points, and these are the models that were violated. So in this case, you have 2 nodes, so 1 source, 2 nodes, Ellis and Bob, and we violate the locality. And the points were here, so they are outside the region where they're supposed to respect the locality assumption. And this happens for all the other cases. So this is the case for the locality. The points are here, they are not respecting, they perform a violation of locality when you are assuming that you have 2 different sources, okay? And well, here you can observe all the combinations that we perform, okay? In the first table, the first line, the first column is the number of sources. So we perform up to 4 different entangled sources. This was the number of the combinations. So we perform the bilocality, for instance, considering the different combination of the sources. And here at the final column, you observe the violation obtained. Okay. When the measurement that we performed were 2. Okay, so k equal 2 for all the places. In the case of the increasing number of sources and also increasing number of measurement settings, we perform up to, as I told you before, up to 1024 different measurements. So we exploited 4 sources, 4 measurement settings at each party. The observed violation was 3.13 in this case. The classical limit was 3, so we violate the classical framework. And this is in very good agreement with the results that we expected from the noises involved in the experiment, because we have optical fibers, the measurements are not perfect, and that's why we cannot reach the maximum value. Well, the summary and the perspectives are and the fact that we experimentally implemented a network with 4 different sources. With increasing number of sources, increasing number of measurement settings, we were able also to certificate the non-local correlations among all the parties. So we were able to observe a violation of Bell inequalities for the bilocal case, trilocal case, and also the tetralocal case. The perspectives are the fact that we can also perform machine learning algorithm in order to characterize the correlations, because in this case you have 4 different laboratories. You can change the situation, you can connect another laboratories or change the way in which the photons are being distributed, and then you can check through machine learning technique, which is the network, for instance, or to ensure the correlations that you are obtaining are really quantum or not. You can also move to more complex networks, for instance, the linear one or also the triangular network. Okay, so that's all. Thank you for the time.
So thank you, Gonzalo, for this very interesting talk. So we are almost over time, but we have 3 questions actually. So the very first one is, how does establishing violations of your inequalities in these networks relate to our usual understanding of bipartite entanglement, like standard Bell inequalities? Can we bound bipartite entanglement across different bipartitions from these measurements?
Yeah, of course. I mean, actually we did it. So we were exploiting 4 different laboratories, and the fact is we proved the bilocality, for instance, between all the possible combinations. So when we were doing, for instance, the maximum, the more complex case, the one of all the sources, all the possible measurements, we ensured that each source was able to violate the Bell inequality singularly, at the single case, and then in parties, for instance, the bilocality and also the trilocality case. So you can, it's like you have a big space, but you can also check for the boundaries of the bilocal case and the trilocal case, which are contained in some way. So it's possible.
Mm-hmm. So another question is, based on the outcomes of these measurements, if we obtain a violation by a certain amount, what can we say about the potential usefulness of the resulting states for applications in communications or computation?
Okay, this is a nice question. So the fact that you have a violation means, I mean, the violation of Bell inequalities are very good for this, because they ensure they are device independent. So you don't have to rely on your system. You don't care about your system. If you have a violation, it means that you have truly quantumness. So the output of the system can be exploited at the moment. I mean, if in the moment that you, for instance, you obtain the violation of the inequality, and some of these numbers can be also exploited for the generation of random numbers, because they are completely random. They were generated through quantumness. So the fact, if you have violation, you can already obtain an application for this output. You can also ensure, for instance, communication between the parties. Since you have a network, you can exploit a QKD protocol. Of course, then you have to check for the conditions of a powerful QKD protocol. So you have to ensure a maximum amount of noise. And then you need, for instance, a high violation if you want to be sure that you can exchange a safe key, for instance. But fundamentally, if you have a violation, you can already, I mean, with a good error, you can already start to exploit this number for something, QKD, randomness, or what you desire.
Mm-hmm. So we have a question from Manuel Morgado in the YouTube chat that would like to know if you could also check these inequalities in butterfly networks.
Yeah. You can check these inequalities in different systems. You don't, I mean, triangle, squares. So that's the idea of this network. It's very easy to change the configuration. You can also check for the butterfly network, and then you have to rely on particular programs or techniques in order to find inequality. Once you find inequality, you can implement the network, and then you can move forward in order to violate this and look for some useful application. But yeah, if you are able to construct something, you can just move forward and try to implement this. With this separable measurement, it's very easy. I mean, you don't have to rely on complex measurements. So yeah.
And then, because we go over time, just a very last question. So the obtained violation seems independent on n, the number of sources. So this is rather unusual in terms of scaling with local errors. What is limiting the strength of the violation?
Okay, so what is independent on the number of nodes? It's not the violation, it's the upper bound. Okay, so of course the violation depends on the number of nodes and depends also in the number of measurements, but the upper bound depends only on the number of measurements. Okay, so no, it doesn't depend on the node, depends on the nodes, but the upper bound only on the number of measurements that you can perform in your system. That's so yeah.
So with this, I think we have to stop. Thanks very much, Gonzalo, for your talk, and also Ryan and Jessie. And with this, I hand over to Christian.
Yeah, many thanks again, Jessie, Ryan, and Gonzalo for your contribution to today's quantum science seminar. And I just want to announce next week where we have Dieter Jaksch from Oxford speaking. Also, the website quantumscienceseminar.com has just been updated to the lineup of the next weeks. And what remains to be said that this Friday, the virtual AMO seminar of our US friends and colleagues starts again for 21 with Thierry Lahaye about quantum simulation of spin models with 200 Rydberg atoms. And as usual, we highly recommend that you watch this one. And with this, we say goodbye until next week.